Hi everyone. So thank you all for coming to the second and final ham radio workshop. My name is Shreya Lingam.
And my name is Connor Hamilton.
So if everyone could just take a moment to sign in using the QR code, that'd be great.
We'll give you guys about 2 minutes to sign in. While you guys are signing in, I want to bring your attention over to the right-hand side. You guys feel free to chime in, type in any questions you might have for us. And as we go through this technical workshop, feel free to answer the questions that we have in the chat box. And we'll try to keep track of who's saying what, and we'll go over the answers as we go through the PowerPoint.
Okay, so we're gonna go ahead and move on. So this workshop is hosted by the IEEE UTD Technical Committee, which strives to help our members cultivate their technical engineering skills through various workshops. You can join the Discord to learn more about the Technical Committee, and you'll also be notified of any upcoming workshops that you can attend. So, what is ham radio? Ham radio is a popular hobby and service in which radio frequency spectrum is used for non-commercial message exchange, wireless training, radio sport, emergency communication, and more. There are 3 classes of licenses that individuals can get: the technician, the general, and the amateur extra licenses. The technician class license is the entry-level license, which gives the individual the ability to access all amateur radio frequencies above 30 megahertz and the ability to participate in local communication. The general class license allows for worldwide communication, and the amateur extra class license allows for individuals to use all bands in all modes. So how can you get licensed? Before COVID, exams were held in person by local radio leagues. By local radio leagues and examiner teams, which consist of several members from a local amateur radio league. So currently, this examiner team will be supervising a test taker through a video conferencing platform like Zoom. The online exams are set up so that you'll be able to take the test on one device, where proctors will be monitoring your screen, and on another device, like a phone or a tablet, will be used to show you actually taking the exam. So you will need a US mailing address, like a residential address or a PO box, and a FRN, which is an FCC identification number. So if you do not have a social security number, then you will need to register for an FRN before the exam, which can be done through the FCC website. If you do have an SSN, your FRN will be issued after the exam. Specifically for the technician class license, which is the entry-level license exam, the test will consist of 36 multiple choice questions that will be pulled from a test bank that is already made available to everyone on the ARRL website. To pass, you will need to get 26 questions correct, which is a 74% on the test. The test itself will take 15 minutes, but with an online exam format, it can take up to 45 minutes for the proctors to relay information and rules. It is recommended to study about 10 hours for the exam by the ARRL, which is the National Organization for Amateur Radios, and the exam itself costs $15. So if you want to get additional licenses, such as a general class license, you can take the technician class license exam and then take the general class license exam on the same day. So if you want to get the highest class license or the amateur extra class license, you will still need to take the technician and the general license exams before. So now we're going to go over some sample questions, practice questions that are pulled from a test bank that's available on the ARRL website. And these questions could potentially appear on the technician class exam because the questions would be from the exam would be pulled directly from the test bank. So I'm going to hand it over to Connor now.
Yeah, so I'll begin these general information questions. We'll then move on to calculation and technical questions, and then we'll end with some circuit diagram and schematic questions. So for the first question, the question reads, what term describes the number of times per second that an alternating current or AC current reverses direction? So I'll give you guys about 15 seconds to think about this and give us maybe an answer, and then we'll go over it. All right, so you guys might be familiar with this one. The answer is D, frequency. So anytime we take the inverse of time, it's going to be frequency. How many times does something happen per second? Anytime, regardless of the kind of question that you're getting, the answer to that is frequency. So we'll move on to the next question, which reads, electrical power is measured in which of the following units? So I'll give you another 15 seconds. So you guys probably know this one as well. The answer to this one is B, watts. Watts can be found to be voltage times current, and that's how we measure energy power in a system. The next question, what is the name for a current that flows only in one direction? So I'll give you guys a few seconds to think about this one as well. Okay, you're probably thinking, Connor, these are pretty easy questions. The point of going over some of these easier questions is to ensure that you understand that don't overcomplicate these questions. The answer to this one is direct current. So you have AC current, you have DC current. One direction and singular line, that's going to be a direct current. So we'll move on to the next one, which is a little more specific to the test, but you'll find this one in the test study manual. How soon may you operate a transmitter on an amateur service frequency after you pass the examination required for your first amateur radio license? So again, I'll give you guys a few seconds. All right, and the answer to this one is as soon as you see your name and call sign appear in the FCC ULS database. You'll be able to go online, view your status, and as soon as you see your name there, you'll be able to just start going. All right, we'll go to question 5. When using a directional antenna, how might your station be able to access a distant repeater if buildings or obstructions are blocking the direct line of sight path? Like I said, if you guys have any thoughts or if you guys think you might know the answer, feel free to throw it into the chat over on the right-hand side. So the answer to this one is B, try to find a path that reflects signals to the repeater. This is a little more technical of a question, but the idea is buildings, even people, we can absorb these signals. So something being in the way of receiving the signal can actually harm your ability to receive it. So trying to find a path that reflects the signal back to you would actually be the best way that you can overcome that. And finally, we'll go to question 6. And question 6 reads, what part of the atmosphere enables the propagation of radio signals around the world? All right, and the answer to this one is C, the ionosphere. So for the next, the rest of these general questions, I'm going to pass this back over to Shreya. She'll finish us up on this one, and then we'll go to calculation.
Okay, so question 7. Which 23 centimeter frequency is authorized to a technician class operator license? I'll just give everyone 10 seconds. Okay, the answer is B, 1,296 megahertz. So for the technician exam, one of the important formulas to memorize is that the wavelength in meters is equal to 300 divided by the frequency in megahertz, and that 300 just comes from the speed of light. But the speed of light is like, I believe 3 times 10 to the 8, but once you convert the units. So again, wavelength in meters is equal to 300 divided by the frequency in megahertz. So after manipulating the equation, you can get that the frequency in megahertz is equal to 300 divided by the wavelength in meters. So if you plug in the numbers, 300 divided by 0.23 meters, remember to convert the centimeters to meters, you will get approximately 1,296 megahertz. And one thing to note is that you will be given a calculator on this exam. So moving on to question 8, which is a commonly accepted value for the lowest voltage that can cause a dangerous electric shock? I'll give everyone 10 seconds again. Okay, the answer is B, 30 volts. So this is just a fact that has to be memorized to answer this question. So just remember that 30 volts is the minimum voltage that is a shock hazard for people. So moving on to question 9. What is connected to the green wire in a 3-wire electrical AC plug? So I'll give everyone a few seconds to answer. Okay, so the answer to this is C, safety ground. So here's a little diagram. So in standard electrical cables, there are 3 wires. The black wire is the source or hot wire, the white wire is the return, and the third wire can either be bare or green, with the green wire being the safety ground. So you can see in this diagram, the green wire is connected to the equipment ground, and the purpose of this green wire is to prevent accidental shocks. So just remember, green means ground. So moving on to question 10. What frequency range is referred to as HF? I'll give everyone a few seconds to answer. Okay, the answer is C, 3 to 30 megahertz. So there are 3 different parts of the radio spectrum, HF, VHF, and UHF. HF stands for high frequency, and it is the range of radio frequency electromagnetic waves between 3 and 30 megahertz. And actually, HF frequencies are the least commonly used by amateur radio operators. So moving on to the next question. What are the frequency limits of the VHF spectrum? Okay, the answer is B, 30 to 300 megahertz. So VHF stands for very high frequency and is the range of radio frequencies from 30 to 300 megahertz. And this range also corresponds to wavelengths of 10 meters to 1 meter. So an interesting thing of the VHF spectrum is that it contains the popular 2-meter band, which is often used by amateur radio operators, because the 2-meter band is at a frequency of 144 to 148 megahertz. So question 12. What are the frequency limits of the UHF spectrum? I'll give everyone 10 seconds to answer. So the answer is A, 300 to 3000 megahertz. So UHF stands for ultra high frequency, and it refers to the radio frequencies in the range of 300 to 3000 megahertz, or 3 gigahertz. So this is also referred to as the decimeter band because it corresponds to wavelengths of 1 meter to 1/10 meter, or 1 decimeter. So basically these past three questions, we've learned that HF is 3 to 30 megahertz, VHF is 3300 megahertz, and UHF is 300 to 3000 megahertz. So moving on to the last general information question, how would you change a dipole antenna to make it resonant on a higher frequency? I'll give everyone 10 seconds to answer. Okay, the answer is C, shorten it. So the important thing to take away from this question is that the antenna length is directly related to the wavelength and inversely related to the frequency. So to make the frequency higher, the wavelength must be shortened and the antenna length must be shortened. So to make it resonate on a higher frequency, you would need to shorten the antenna length. So now I'll hand it over to Connor to go over some calculation and technical questions.
All right, thank you, Shreya. Awesome job. So I'll start off the first calculation and technical question, which is what is the correct way to connect a voltmeter to a circuit? And again, I'll give you guys about 10 seconds. We got in series with the circuit, in parallel with the circuit, in quadrature with the circuit, and in phase with the circuit. All right, if you guys said in parallel with the circuit, you'd be correct. That's answer B. And the reason is, obviously we know in parallel, voltage stays the same. So that's the best way to connect a voltmeter to the circuit to get the accurate voltage. So we'll go to the next question, which reads, what is the current flowing through a 24 ohm resistor connected across a 240 volt, or sorry, connected across 240 volts? I'll give you guys about 10 seconds again. All right, if you said 10 amps, you're correct. That's answer C. It's very simple, voltage divided by current. So 240 divided by 24 is 10. If we go to the next slide, we'll actually be able to see a little voltage, current, power, resistance wheel. And I encourage you guys to look this up on your own as well. It's a really helpful wheel for calculations and figuring out, like an ENA, this is a great thing to have, especially in your physics classes too, if you guys haven't taken those yet. But basically, these shows the relationships between the different values and options that you have in Ohm's law. And so how you calculate based on whatever you're looking for. So we'll go to question number 3 for the calculation questions. And it reads, what formula is used to calculate resistance in a circuit? I'll give you guys about 10 seconds. All right, and you guys probably got it from the previous one as well. To calculate resistance in a circuit, we're going to do voltage divided by current, which is answer B. And again, I'll just refer you to that wheel above. Ohm's law is one of the best things you can know as an EE or CE student. So question number 4, it reads, how much power is being used in a circuit when the applied voltage is 13.8 volts DC and the current is 10 amps? All right, and again, you know, we look at that wheel. We're looking for power. We have volts and we have current. So voltage times current equals power. 13.8 times 10 is 138. That's answer A. So we'll go to the next one, question 5, which is if a frequency readout calibrated in megahertz shows a reading of 3.525 megahertz, what would it show if it were calibrated in kilohertz? All right, and you guys probably know this one. It's 3 orders of magnitude higher. So we're looking at a change to the 10 to the third, right? So 3.525 megahertz equals 3,525 kilohertz, or option C. And then finally, for question number 6, what is the amount of change measured in decibels of a power increase from 20 watts to 200 watts? So is it 10 dB, 12 dB, 18 dB, or 28 dB? All right, and if you guys said 10 dB, you'd be correct. That's answer A. If we go to the next slide, we'll be able to see, so decibels are actually relative units of measurement at log scales. So they're used to measure one power over another. So if we have milliwatts and we're looking for dBm, we would use 10 times the log of the power in milliwatts. Similarly, if we have 2 different measurements, so 20 to 200, we would divide the 2, and then we would use that power in the equation. Similarly, if we had dB, we would do 10 to the power in dB divided by 10 to get watts or milliwatts. So another way to think about this is for every wattage increase by 2 times or a change by half, there's a change in plus or minus 3 dB. So let's go back up to the problem again, and we'll be able to see, okay, a power increase from 20 watts to 200 watts. So remember, every time we increase by 2 times, we've gone up 3 dB. So 200 times what is, 20 times 200, 20 times what equals 200? So the answer to that is 10. Every time we go up by a measurement of 10, that would be a 10 dB increase. Or if we go down by 1 order of magnitude, that would be a 10 dB decrease. So these are 2 ways to think about the same thing. And I encourage you guys to try those calculations out. This is not an easy concept, but once you get it, you got it. And if you guys are interested in RF applications and circuits, you guys will want to definitely know this. So as we go on to question 7, I'm going to give it over to Shreya to finish us out in these calculation questions.
Thank you. So question 7, which of the following precautions should be taken when measuring high voltages with a voltmeter? I'll give everyone 10 seconds to answer. Okay, the answer is B. Ensure that the voltmeter and leads are rated for use at the voltages to be measured. So this is an important question because it directly relates to safety. So when you're measuring high voltages, it's important for your safety that you ensure that the meter probes, leads, and the insides of your meter can handle the high voltage without conducting that voltage to you. So we can just start eliminating answer choices too. That's an alternate method we could solve this is. So voltmeters have a high impedance so that they don't affect the circuit that you are measuring. So answer choice A is wrong. Answer choice C is wrong because you want to measure the voltage difference between the ground and the circuit, and you don't want to ground the high voltage through your meter because then it could potentially blow up your circuit or meter. Answer choice D is wrong is because you want your voltmeter to measure a range of RF frequencies. So moving on to question 8. What is probably happening when an ohm meter connected across an unpowered circuit initially indicates a low resistance and then shows increasing resistance with time? I'll give everyone 10 seconds to answer. Okay, the answer is B. The circuit contains a large capacitor. So the voltage is 0 with an unpowered circuit, but as current is applied, the capacitor will charge up past the current freely and give a low resistance to keep the voltage at 0. As the capacitor charges more, there is power stored inside of it until eventually the capacitor is full and no longer allows current to flow through it until the voltage source is removed. So at this point, the capacitor will try to keep the voltage at the new equilibrium value. So moving on to question 9. If the averaging time for exposure is 6 minutes, how much power density is permitted if the signal is present for 3 minutes and absent for 3 minutes, rather than being present for the entire 6 minutes. I'll again give everyone 10 seconds to answer. Okay, the answer is C, 2 times as much. So first of all, let's define power density. So the power density is the amount of energy absorbed from the radiation per unit of time from a distance squared. So basically, the amount of energy absorbed is the power density times the exposure time times the distance squared. So now we can just rearrange that equation. So the energy absorbed equals the power density times the time times the distance squared. So let's calculate the amount of energy absorbed during both of these time intervals. So for the 6-minute average exposure, the energy absorbed is the power density times 6 minutes times the distance squared. And we don't know what exactly the power density is, and we don't know the distance. So we can just refer to it as 6 times power density times distance squared. So if the same signal was applied for 3 minutes on and then 3 minutes off from the same distance, the energy absorbed would be the power density times 3 minutes, for which the energy was absorbed for, times the distance squared. So 3 times power density times distance squared. So when comparing these two values, it can be seen that the energy absorbed during the 6 minutes of exposure is twice that of the energy absorbed during the 3 minutes on and 3 minutes off. So the formula to remember for this problem is that the energy absorbed from the radiation is the product of the power density, the time, and the square of the distance. So moving on to question 10. Which amateur band are you using when your station is transmitting on 146.52 megahertz? So I'll give everyone 10 seconds to answer. So the answer is A, the 2-meter band. So in a previous question, I'd mentioned that the important formula to memorize for these types of questions is that the wavelength in meters is equal to 300 divided by the frequency in megahertz. So this question gives you the frequency in megahertz, so you can just plug in the numbers. So 300 divided by 146.52 megahertz, and this is going to be around 2 meters, which is the wavelength. Moving on to question 11. What is the proper location for an external SWR meter? So I'll give everyone 10 seconds to answer. Okay, the answer is A, in series with the feed line between the transmitter and the antenna. So first of all, what does SWR stand for? So SWR refers to the standing wave ratio, and this has to do with how well the radio frequency signal matches the impedance of the input to the output. So usually an SWR meter is placed close to the transmitter so that you'll be able to check if the antenna and the transmission line, which forms the antenna system, matches well with the transmitter. So an SWR meter would be placed in series with the feed line in between the transmitter and the antenna. So moving on to question 12. What is the approximate length in inches of a quarter wavelength vertical antenna for 146 megahertz? So we'll give everyone 10 seconds to answer. So the answer is C, 19. So you've probably already heard this formula way too often. I've probably mentioned it way too often. But again, the magic formula is the wavelength in meters is equal to 300 divided by the frequency in megahertz. Just knowing this formula will help you with a lot of the questions because these types of frequency, wavelength, and converting in between questions appear a lot. So you can just plug in the numbers. So you would get 300 divided by 146 megahertz is approximately equal to 2 meters. Okay, but we're not done here because it's asking for the length in inches. So now we can convert 2 meters to inches. So 1 meter is approximately 39 to 40 inches, so 2 meters is around 80 inches. But one thing to note is that it's asked for a quarter wavelength. So then a quarter of 80 inches would be 20 inches, and the closest possible answer is 19. So here's a similar question. What is the approximate length in inches of a half wavelength 6-meter dipole antenna? I'll give everyone 10 seconds to answer. Okay, the answer is C, 112. So this is even easier than the previous problem because here you're already given the wavelength in meters. So you can convert the wavelength in meters to the wavelength in inches. So remember, 1 meter is approximately 39 to 40 inches. So 6 meters would approximately be 6 times 40, or 240 inches. But if you pay attention, it says a half wavelength dipole antenna. So you have to take half of the wavelength in inches. So 240 inches divided by 2 is 120 inches, which is closest to answer choice C, 112 inches. And you will be given a calculator for these questions. So now we're going to move on to some schematic questions, and I'll hand it over to Connor.
All right, so this is going to be one of the, as EE and CE students, in my opinion, one of the best places that we can get points. So definitely pay attention. You may not struggle with a lot of these, but knowing these can be, especially when it comes to just previous knowledge that you've known, one of your best helps throughout the exam. So we'll go to the first question. And the first question reads, what kind of switch is represented by item 3 in the figure below, or to the figure to the right? So is it A, a single pole, single throw, B, single pole, double throw, C, double pole, single throw, and D, double pole, double throw? So I'll give you guys about 10 seconds. All right, and we are looking at number 3, and that would be a single pole, single throw. So since we're looking at a switch here that's not going anywhere else, and it's only got one little switch mechanism there, we're looking at single pole, single throw. So that's the easiest way to think about that. All right, let's go to question number 2. Question number 2 reads, in the circuit diagram to the right, what is the purpose of component number 2? So is it A, to give off light when current flows through it? Is it B, to supply electrical energy? Is it C, to control the flow of current? Or D, convert electrical energy into radio waves? All right, and some of you, especially if you've been through electronic devices, you guys have already started on this. Component number 2 is a transistor. The easiest way to identify a transistor is a 3-terminal device. So you can see it's got the 3 terminals coming into it. You've got a circuit path going from the top, circuit path from the line in the middle, and then you have a ground there at the bottom. And so what a transistor does is it amplifies electrical signals, so it controls voltage and current. So in this case, we'd be using it to control the flow of current throughout the system. So we will move on to question number 3. Question number 3 reads, what is component 4 in the figure to the right? I'll give you guys about 10 seconds. As I read this out, is it number A, antenna? Is it letter B, a transmitter? Is it C, a dummy load? Or is it D, ground? So if you guys said antenna, you'd be correct. Easiest way to identify antennas, especially in schematics like these, it looks like an upside down ground with a line through it, basically. I'm sorry, a right side up ground with a line through it, basically. So you can see that out on the other side of that variable capacitor there, you have what looks like it could be a ground, but it's got a line through it. That is an antenna, and those are one of the most important things in RF circuits. All right, so now we're going to move on. Question number 4, what type of receiver is shown in the figure to the right? I'll give you guys about 10 seconds to look over those and look over that schematic. All right, and this one might be a little more tricky. So what type of receiver is shown to the right? It is a single super heterodyne. So how am I supposed to know what a single conversion super heterodyne receiver is? A single super heterodyne receiver shifts signals to intermediate frequencies. So if we look at that component in the middle, that intermediate frequency amplifier, we can see that it shifts all those intermediate frequencies. So we're looking at letter C, and that is one of the best ways to identify that. All right, let's go to the next one. All right, number 5. What type of circuit is shown in the figure above if block 1 is a frequency discriminator? While you guys are thinking about that, is it A, a double conversion receiver, B, a regenerative receiver, C, a super heterodyne receiver, or D, an FM receiver? All right, and it is letter D, an FM receiver. And one of the best ways to know this, because this is another schematic that might trip you up, is a discriminator demodulates FM frequencies. So you notice that that signal has to go through block 1. And if it's a discriminator, then it's demodulating that FM frequency. Therefore, it has to be an FM receiver. Finally, let's go to the next question, number 6. And number 6 reads, what is component 2 in figure T1? So I'll give you guys about 10 seconds to look over this one. All right, and you're probably thinking to yourselves, hey, I've only gotten over this one already. Yeah, so this is letter B, a transistor. And again, one of the best ways to identify a transistor, if you aren't already familiar with one of these components, is that they're 3 terminal devices. And the only 3-terminal device here is component 2, therefore it's a transistor. So I'm going to hand this back over to Shreya to finish this up.
Okay, so question 7. What is component 4 in figure T2? A, a variable inductor, B, a double pole switch, C, a potentiometer, or D, a transformer. So I'll give everyone 10 seconds to answer. Okay, so the answer is D, a transformer. So a transformer is composed of 2 inductively coupled coils that are not connected directly to each other. So when looking at the schematic, you can see in component 4, there's a coil representation on either side with 2 lines in the middle. And these 2 lines represent that the coils are separated, they're not connected. So that's the best way to be able to tell, because this is a transformer, because there are coils that are not connected directly to each other. So moving on to the next question, which of the following is accurately represented in electrical schematics? A, wire lengths, B, physical appearance of components, C, the way components are interconnected, or D, all of these choices are correct. So I'll give everyone 10 seconds to answer. The answer is C, the way components are interconnected. So a circuit diagram is basically just a graphical representation of an electrical circuit. So specifically a pictorial circuit diagram uses just simple images of components, while a schematic diagram uses standardized symbolic representations of components. And this will show the interconnections of the circuit. So an example to this schematic diagram was seen in a lot of the previous questions that Connor went over. So moving on. Which of the following is a resonant or tuned circuit? A, an inductor and capacitor connected in series or parallel to form a filter. B, a type of voltage regulator. C, a resistor circuit used for reducing standing wave ratio. Or D, a circuit designed to provide high fidelity audio. So I'll give everyone 10 seconds to answer. Okay, the answer is A. An inductor and a capacitor connected in series or parallel to form a filter. So first of all, what does resonance even mean? So resonance refers to when the effects of the capacitance and inductance are the same and opposite. So stored energy is passed from the inductor to the capacitor. So at a certain resonant frequency, the impedances of the capacitor and the inductor cancel each other out. So the impedance of the circuit is just equal to the resistance value. So answer choice A is the only one that mentions capacitance and inductance, which is required to have resonance. So that would be the only possible correct answer. So moving on, what class of electronic components uses a voltage or current signal to control current flow? A, capacitors, B, inductors, C, resistors, or D, transistors. So I'll give everyone 10 seconds to answer. The answer is D, transistors. Okay, so this is the third question that involves transistors. So obviously this exam really likes transistors as an option choice or testing over transistors. So just a little recap on transistors. They are semiconductor devices used for amplifying, controlling, and generating electrical signals. Okay, so moving on. What is the name of a device that combines several semiconductors and other components into one package? A, a transducer, B, multipole relay, C, an integrated circuit, or D, a transformer. So I'll give everyone 10 seconds to answer. Okay, so the answer choice is C, an integrated circuit. So an integrated circuit, or IC, is a microchip that contains various components or circuits inside. It's all integrated into a single unit. So they're just miniature active devices containing components like transistors, diodes, passive devices, such as capacitors and resistors. And their interconnections are just built on a thin semiconductor material like silicon. So for the last question that we're going to go over today is, which of the following can be used to display signal strength on a numeric scale? A, a potentiometer, B, a transistor, C, a meter, or D, a relay? And I'll give everyone 10 seconds to answer. Okay, so the answer is C, meter. So this is a pretty straightforward question. A meter is just a device that measures the quantity and displays the results on a numerical scale. So this question is pretty just straightforward. So I'm going to hand it back over to Connor to wrap us up for this evening.
All right, guys. And so, we'll go to the next slide and we'll see all these different websites. We wanted to provide you guys with some self-study material. We can go over questions all day. Just like in class, you guys could study the answers all day and maybe get lucky and maybe that's the answers, or maybe that's the questions that you go over in class for the test. But in general, if you guys are studying on your own and you guys are reading on your own and doing some self-study, you'll find that you'll learn a ton more and you'll be empowered to be able to really use amateur radio to get a lot better at this stuff, and you'll just do a lot better in your classes as well, especially if you're interested in something like RF engineering, which is directly related to getting your ham radio license. We had gone over it in one of the previous workshops, but one of the best ways to get involved in RF engineering is to begin by getting your ham radio license. So the first three websites, the first is just the Amateur Radio Relay League. They provide some test materials, some study materials, ways to get involved, and some things that you can do to better your knowledge. The two websites below the first website, which are both ARRL designated websites, are study materials. So you guys can go to these websites, you can study on your own in these test banks, and hopefully by the end of the summer, next fall, we're back in person, and we'll be able to provide you guys with some great resources and more technical workshops that we can go over directly related to having gotten your ham radio license. We'll be able to use that to get into all sorts of cool stuff that we can build and learn more about all this cool stuff. DallasRaces.org is what it looks like is next, and that is just a good way. Amateur radio is an awesome way to stay connected, especially in disaster situations. Amateur radio keeps going during all this time. If you guys think about back in when we all lost power in the February winter storm, amateur radio kept going, and it was a great way for people to be connected to one another, knowing who did and did not have power, and where first responders could go, and where people who didn't have any power could go for shelter and for supplies. So that's a great website to go to, and that's just also a tangible way to see, getting this license directly relates to me helping my community in an engineering type of environment, which we're all getting our degrees, and so that's a really fun way to give back and to be involved. And then finally, we end with two websites at the bottom that also help our studying. So the next slide, learn more about technical committee. So we meet Thursdays at 11:30 a.m. and we basically talk about stuff like this. We talk about what do we want to learn more about, what do students want to learn about, what kind of programming things can we do, what kind of hands-on hardware things can we do, how can we challenge ourselves to be better. We learn a ton of theory in class, and ultimately that's great, but being able to put our hands on something and be able to create something is a skill that employers want. And that's why technical committee is so great. A little bit about me, and I mentioned this in the previous workshop, but I'm coming back to get my degree. I don't have a ton of technical knowledge, and being an engineering student, I was very intimidated. And technical committee was a great place I could go, and I didn't feel nervous. People wanted to help me, and now I want to be able to give that back, and I hope you guys agree. That's a great way that we can help each other out, help each other learn, and help each other succeed. So again, those are on Thursdays at 11:30. Anybody is welcome. You guys come. Tell us that you want to sign up through Discord, and we will point you in the right direction. So we'll go to the next slide, and that's about Comet Hack. So April the 23rd through the 25th, we will be putting on Comet Hack UTD. So that will be a formed team of 1 to 3 people for a 36-hour challenge where you guys can network with people, create these awesome programming things, and you can win prizes. So it'll be a blast. Like I said, 36 hours of just a ton of fun. So please sign up. You can register at comethack.org, and you can also look it up on the social media. All right, guys, that is it. So if you guys have any questions, I'd encourage you type them in the chat. Feel free to reach out to us via Discord or to the technical committee. But we really appreciate you guys sticking around. We'd encourage you guys, like we said, to get licensed. And when we see you guys in the fall, we're going to have a bunch of cool technical committee workshops for you guys. We'll stick around a little bit in case you guys have any questions. Otherwise, y'all have a great weekend.